This problem is a continuity problem. Basically, if I look at either of these two functions, the minus x plus 2 or the x squared minus 3, both of those functions are really obviously continuous. There's no holes, there's no division by zeros, there's no square roots, nothing problematic about them. The only possible candidate for them to be a problem is at the value of 3. So I'm going to first do it from the left, which is exactly what I said. And if I go from the left, which is this minus x plus 2, then what am I doing? I'm doing minus of minus 3 plus 2, which is 5 in total. And then if I go the other side and look at the limit as x goes to minus 3 from the right, if I'm going from the right, then I'm looking over here at this x squared minus 3 business, in which case I'm doing minus 3 squared minus 3, which is equal to the value of 6. So in this specific example, when I go to my problem spot of minus 3, and I go from the left, it gets the value of 5, and when I go from the right, I get the value of 6. And so they don't match. At that minus 3, the limit from the left and the limit from the right do not match. It is a jump discontinuity, and so we can say that the answer is does not exist. All right. And so I'm going to keep on moving along here, but as I go along at any point like this, just say, hey, if you've got any questions, if my explanation didn't make any sense, just let me know. But next up, we're going to do question number 12. I'm going to ignore the one says to do it in order. We'll probably hit maybe all of them, but I can sort of jump around and try to hit the ones that are, I don't know, highest priority first, at least as you guys conceive of highest priority. Ah, okay. I like this problem. You always have to word these. So this is a net chain problem, and I can sort of tell that right away. Anything that tells you an initial population and then a change, that's one of these net population ones. But there's a couple of different things to pay attention to. Do you just care about the total change? Do you care about the final value? Are you supposed to be adding the initial value, subtracting it, ignoring it? There's a bunch of varieties that come. So let's read this one carefully. It says, the population of a bacterial colony is changing at a particular rate. So this here is a derivative. When you see the word rate, that is a signal that says it is a derivative. So the initial population is 600 cells. And what it is asking for is what is the population after the first hour? So if I'm interpreting this correctly, you start with 600, you go away for 1 hour, and then you have some presumably higher number than that. So the formula that we use for when it is not the net change, it's the final population, so 600 plus whatever the net change is going to be. So the formula is going to be 600 plus the integral from 0 up to 1 of whatever this rate of change is, minus 100 over 1 plus t squared dt. Okay. And that's going to be equal to the final population. So read these carefully. The big sort of difference maker is, do you have to include that 600 or do you not? And it depends on the wording of the problem. In this case, we ask for what is the population after 1 hour. We want to include the 600. If it said, how much is the population changed, you wouldn't include the 600. All right. Well, now we have to actually do this integral here. So how do we do that? A couple different things to think about. We'll get some colors over here. All right. First of all, is this a U-sub or is this sort of one that you can identify? For example, if it was 1 plus t squared, but without the brackets, you'd say it was an arctan. But in this case, I think it's a U-sub. That 1 plus t could be our u, and then everything could change. So let me set my u to be the 1 plus t. My du is therefore just equal to dt. And if I also want to change my limits of integration, so if I plug in the 0 here for the t, I get the value of 1. If I plug the 1 in, I'm going to get the 2. And so if I put all of that back together, then what I'm going to get is the 600 plus an integral now from 1 up to 2 of minus 100 over u squared du. All right. Okay, so that's not going so badly. Now I actually know how to do that. Sorry, my monitor is sometimes a little bit choppy here. It cuts out black for a second, that's why. All right, so 600 plus, well, I'm going to put all of that minus 100. U cubed I know goes to U to the power of -1. And then when I take its derivative here, it would bring out another -1. So I'll take the minus that was out the front, and I'm going to put a plus there. And then it's going to be evaluated between 1 and 2. All right. So this is going to be equal to the 600. So 600, and then it just died again. Okay, now it's back. 600 plus the 100, and then if I plug this in, this is going to be the value of 1/2 minus. The 100 was a negative, but I had another negative that came about. It was that when I integrated the u to the -2, it went to u to the -1 divided by -1. That second -1 made it the original -1 to a positive. All right. So somebody tell me in chat, what should we go to next? Question 13, yes, and please do use the everyone version of the chat. Okay. This one, I'll be honest, is you either see it or you don't. So there's two different derivatives of arctrig functions you need to know. One of them is that the derivative of arctan is 1/1 plus x squared, and the other is that the derivative of arcsin is 1 over the square root of 1 minus x squared. Those are the two you have to know, and it's just a question of, do you see it or do you don't? So when I see this and I see 4 over t squared plus 1, it just screams out arctan at me, and so I just say, okay, that's what it's going to be. So in particular, I am going to say that this is 4 times arctangent of x between the values of 0 and 1. In other words, 4 times arctan of 1 minus 4 times arctan of 0. Well, now this gives a bit of a different question, because I have to know, well, what is arctan of 0 and what is arctan of 1? And this is a useful thing to know as well. So the thing that I always do is I remember my 2 different special triangles. The one that's going to be relevant here is the pi over 4, 1, 1, root 2 triangle, although I'll put up on the screen. The other one is that pi over 6, pi over 3, 1, 2, root 3 triangle. Those are the 2 triangles you need to know. They'll tell you all the different trig values you could care about. And in this case, okay, one second. I need a tangent to look like 1. So if I take the pi over 4 value, if I look at this one right here, oops, I look at that guy there, tangent of that is 1 divided by 1. And so this one indeed is going to be 4 times the value of 1. And the arctan of 0 is just 0 because I know tangent of 0 is 0. I know the graph of tan. Tan of 0 is 0, so arctan of 0 is 0 as well. So the answer turns out just to be 4, and it looks like we have that value right there. Okay. Okay, I got my mouse back. Good. Okay, so one second. I got to go back and address this point that Adam was saying because I'm apparently an idiot. Where was it? 12. I think I even said it correctly out loud, but then I think I just did it completely. This one here. Oh yeah, look at me. I even circled it the pi over 4. I said the arctan, and I circled the pi over 4, but look what I did when I actually entered it over here. So I will come down, change my colors again. The arctan of 1 is the pi over 4, and so I get the value of pi, and let me come right there and circle it correctly. Pi. Perfect. We want John Reinhold back. Awesome. Okay. What should we do next? Someone let me know in chat. Where should we go to? Wonderful. So they say sort of a see it or you don't. Just make sure you've got these 2 guys on your formula sheet. And if you see them, then you know what to do with them. All right. Someone let me know. What questions should we go to next? Or if there's any questions on the things that I've talked about already. Number 2. All right. Now, you actually have 2 choices with this one. Well, let's actually see. The question is whether it's going to be 0 over 0 when I plug the number in. If I just plug the number in and I get a value, then it's just whatever that value is. If I plug the number in and I get 0 over 0, then I'm going to have to do a little bit more work to it. So it seems that if I plugged in 3, it would be 5 on the top, and then on the bottom, it would be 3 squared, which would be 9, minus 9, which would be a 0. Okay, so it's sort of loosely of the form 5 divided by 0. So it's going to be an infinity. But what we have to evaluate is it going to be plus infinity or is it going to be minus infinity? Those are the two different cases. So plus infinity versus minus infinity. And I just realized something. Let me just scroll around here. Oh, I am good doing it. Okay. I thought for a moment I wasn't recording, but it turns out I am recording. Apparently, I'm at least a little bit smart. So we know it's the plus or minus infinity one. It's definitely one of those two, but we have to evaluate. Now, how do we evaluate it? Okay, the whole trick here is to look and focus in on this from the left business. So we are going to 3 from the left. So how do we deal with that? Well, that means that when I look at the value of 3 that we have, it's something just a little bit smaller than 3, something like a 2.9, okay? So let's look at this bottom here. And let's imagine if we were doing this. It'd be like 2.9 squared minus 3 times 2.9. This is sort of an example of what that bottom would look like. And in here, the 3 times 2.9 is a bigger value than the 2.9 times 2.9. So this thing is a very close to 0 number, but slightly less than it, slightly negative. And that tells me that it goes to minus infinity because it's negative on the bottom, and since it's going to 5 on the top, 5 over sort of a negative 0, if you will, so a negative infinity. All right. So 1 second, let me just jump in here to the participant list. Somebody's got a sneaky microphone stuck on here.
Hello?
Hello.
Yes!
Let's shut those people up.
Aww.
Do we get them? Oh yeah, they can't say a thing. This is awesome. Okay. Oh, going back to one second. My thing's failed. I see a comment that I'm almost certain to agree with, but I can't get my mouse working again. Just give me one. I have to disconnect and reconnect. I'm sorry. But I'm pretty sure the comment said, I think I said pi over 4 out loud, but then maybe didn't write it down. So somebody says, let's just check this. Oh. Okay. I'm sorry. This silly little thing. Bear me out. It's going to work. I promise you. Question 19. Let's do this. Yes, please use the share with everyone, by the way, in your chat. 18 and 19. Ah, okay. I like this one. Oh, this is a very standard one. I mean, something like question 19, you can probably guess has a very sort of high probability, if you will, of showing up on a final exam. We know that the areas and the volumes are the two big things we have not tested. So I've got two curves, y equals 5 minus x and y equals 4 over x. So the first thing I have to do is graph these. So 5 minus x starts up here at 5, and it's a line that goes down like this, all through those connections. It goes over there. 4 minus x, okay. 4 minus x is that graph. I remember what it looks like. So it comes down here and goes off somewhere like that. I don't know whether these intersection points are even remotely good. They might be completely terrible. Maybe we'll figure that out in a second, but I just sort of gave the rough shape, and then we'll see whether these intersection points are any good. So I can kind of see what my region looks like. My region looks like sort of this thing here in the middle. All right, we'll call that a region. Now, the question is, are my intersection points any good? Probably not, actually. So let's go and figure out how we can do that. Well, to figure out the intersection points, I need to go and set these two curves equal. So I want to set 5 minus x to be equal to 4 over x. Now, how do I do this? The trick is it's actually a quadratic, but it's a quadratic a little bit in disguise, because I've got the x on the bottom here, but I can multiply the x up. So it actually looks like 5x minus x squared is equal to 4, all right? And if I rearrange that again, I will say that it's going to be x squared minus 5x plus 4 is equal to 0. If I want to factor that, I get x minus 1, x minus 4 is equal to 0, and so I get x equal to 1 and x equal to 4 as my two spots. Now you have a little bit of a choice. What I usually do is draw the sketch like loosely or very lightly, figure out the intersection points exactly, and then come back. It just sort of helps make it clear in my mind. If you prefer, you could say, well, no, look, there's no point wasting any time here, Trevor. I'm going to, compute the intersection points first, and then I'll come down and graph it. So I'm now going to draw a better graph now that I know what my intersection points are. I was only loose before. So where does it go through? It goes through the value of when x is 1, y is 4. And so I have to press that button. There's one intersection. Oh, excuse me. Not there. There it is. X equal to 1, y equal to 4. And the other one is x equal to 4, y equal to 1. So those are the two intersection points. So now I can come through and draw them exactly, looks like that, and I have my little region snuck in the middle, right like that. Very nice. Okay. Now it says, write a definite integral that will give the area of this region. So I got to make a little bit of a choice here. And my choice is, do I prefer to use an integral with respect to x or an integral with respect to y? I could do either. Doesn't really matter. There's only one region if it's top minus bottom. There's only one region if it's right minus left, so who cares? But my curves are already written in the way that makes easy to do in terms of x. I don't have to rearrange anything. So I'm going to do an integral with respect to x. That is, I am going to do a vertical strip here. So I will do a vertical strip, and it will be the top minus the bottom when I come and write down my area. So my area equals the integral from 1 up to 4. Those are those two intersection points that we did. And then I'm going to say that it is simply the top curve, which I believe was 5 minus x. That's the top curve, minus the bottom curve, which is 4 over x, and then all of that dx. It says evaluate this definite integral. This is a polynomial. The 4 over x goes to the natural logarithm of x, but I'll let you guys compute out the final value because I get to do that. Because I have a math PhD, so I don't have to bother computing out values. That's my privilege. Tough to be you. Okay, what am I doing next? 20, it says. All right. So, by the way, as I go through these things, please do let me know in the chat. You can turn your microphone back on. I believe you have the ability to override me. Let me know if that's not the case. If I go too fast or I don't explain something well or you just have a question, just bug me about it, but that's fine. Okay. Cylindrical shells and disk method. Wonderful. So let R be the region. Oh, look, last year we graphed it for you. That was awfully nice. Let R be the region in the xy plane bounded by some curve and y equal to 0. And let S be the solid of revolution obtained by rotating the region around the y-axis. Okay, so if we go around the y-axis, it looks a little bit like that. All right. And about the y-axis here. Okay. And what are we doing? Oh, I see. In A, all we're doing is write a definite integral that will give the volume of S. So here's the thing. We have to figure out whether we're doing an integral with respect to x or with respect to y, which is sort of the same thing as asking, are we going to be doing a cylindrical shell method or whether we're going to do a disk washer method. I'm going to make a mistake for a moment. I'm going to suppose that we were doing disk washer. Don't write this down if you're making notes. Imagine that we were doing the disk washer. Okay. So here we'd have to have an outer radius and an inner radius. And your inner radiuses would have to be like x equal to the right side minus x equal to the left side. Those would be your radiuses. But then you have to take this curve here, and you have to solve it for x. But it's a really hard one to solve for x. It's not nice at all. So I don't think that this disk washer method looks very nice. So let's get rid of that. Instead, what I want to do is I want to do the shell method. So I'm going to put a vertical strip there. I write the vertical strip on the mirror, and I come along, and I make a little cylindrical shell. There we are. Now I want to write down an integral for this. How are we going to be doing this? So I'm going to take the volume. Oh, sorry. I'm going to take the volume here is going to be the integral from 0 up to 1. I'm choosing the x value of 1 and the x value of 0 there. That's how I choose 0 to 1. It's 2 pi a radius multiplied by a height and all of that dx. So what is the radius here? Well, the radius is quite simple. My axis of revolution is just the y-axis, so there's none of those like shifts that we often had to do in class. So it goes 0 up to whatever that point is. That's just some distance x. And then what is going to be the height here? It's going to be x minus x cubed, which is the top, minus the bottom, which is 0. And so that's all that is. So that's the value. Evaluate this definite integral. I again refuse and use my professor powers to avoid this. Moving on to B. Now let me know if that doesn't make sense, by the way. Okay. So now we have a new one. Oh, this one time we do make you sketch it. So by the way, may I say one more thing about A before going on? A is one of those examples where it is forced on you. Because you cannot easily solve this equation the other way around, you are forced to use the cylindrical shell method. The other way we can force you into a method is just tell it to you, just be like, use the cylindrical shell. It doesn't take as much thinking, but it does the same result of getting all students giving the same type of answers. Anyways, but this problem here, we haven't drawn the region. So y is equal to 1/3 x. So when x is equal to 3, y is equal to 1. So it looks like that kind of line. And then x equal to 3 and x equal to 6. And that gives me, on the x-axis, so that gives me this region right there. Okay, very nice. Now, what does it do? It wants to write a definite integral for the volume of solid obtained by rotating this line around the region, or this region around the line, y equal to 3. Okay, so here is the line y equal to 3. So if I want to come and have a sort of inversion, you see how this top spot here is the value of 2, which is 1 beneath that. So it starts there and then goes up like that, then has a height of 1, and then over like that, and then over like that. That's what my mirror image of this region looks like. Okay. And then what am I doing? I'm rotating this around the line y equal to 3. So we have a choice. We could use cylindrical shells, or we could use disk washer. So the question is, which is better, cylindrical shells or disk washer? If I use cylindrical shells, that is, I am sort of going around in this kind of way, horizontal strips, then my horizontal strip down here and my horizontal strip over there have different right and left curves. I could do it, but it'd just be kind of gnarly. So I think it is much easier to go like this. And that's my vertical strip, and we're going to do a little disk washer method, and there it fills in just like that. So I think it's a little easier to do it that way. Okay. And then what do we actually want to do? Well, this is the integral from, it looks like x equal to 3 up to x equal to 6. By the way, it's an integral with respect to x because the little width here is a little dx. Much of the way over here, we had a little integral, a little width dx as well. So both of these are integrals with respect to x in this case. I guess we were very nice to you on last year's final exam. And so this time, I need to do pi outer radius squared minus pi inner radius squared, and then all of that dx. Okay, what's the outer radius? Well, for my radius, I need to go from my mirror here all the way down to the bottom. So that is my outer radius here, and it looks my outer radius is exactly the value of 3 because that's where my mirror is. My inner radius, however, is just that. And so it's that full value of 3, but minus this little strip. And this strip, if we remember our equation, was the line y equals 1/3 x. So while the outer radius, the big one, is the 3, this is the 3 minus the 1/3 times x. That is my inner radius. So outer radius over here and inner radius over there. All right, a big question. So let me take just a moment to see if anyone has any thoughts as they catch up. Let me know where we should go to next here. All right, let's do 3. 1, 2, 3. Oh, yes, okay. 3 is a very standard example. It's one of these ones you kind of hope for because I really can't make it any more challenging than this. But it still throws a lot of people just because it's, I don't know, it's just a little bit confusing, I guess. When it's limited infinity, the method is highest power on the top, highest power on the bottom. Okay, so you want to do highest power on the top, highest power on the bottom. But with a square root, that gets a little bit confusing because on the top here, there's a square root of x to the 10. So this is going to be equal to, if I look at what its highest power is, on the top here, obviously the 7x and the 1 don't go wrong. So this sort of looks a little bit like root 9, which is 3, right? Square root of 9 is 3. And then it's like x to the 10 divided by 2, which is sort of the same thing as x to the power of 5. And on the bottom here, it's just going to be x to the power of 5. So this x to the 5 on the bottom, this x to the 10 over 2, aka 5, is just going to be canceling. And so all I get is the value of 3. And so it's just going to be 3. It's about as easy as that. If the power on the top is bigger, for example, x to the 11 here, so the numerator would dominate, and would go to positive infinity. If the power on the was bigger on the denominator, say it was x to the 6th here, then the bottom would dominate, it would go to 0. And then the minus signs could have happened, for example, if there was, a minus somewhere else or anything weird like that. By the way, don't be confused. It's not the first power. In this case, we happen to have written the highest power first, but I don't have to do that. I could write the highest power last or in the middle. So that doesn't matter. All right, so that's all to say about this problem. Next up, we're going towards, oh, I touched my cord again. Oh, no, it was short enough not to disconnect you. Wonderful. 21, let's go. All right. Optimization. Wonderful. I'm glad that we asked this. I was hoping we would do the optimization problem. So this says a right triangle has 2 legs, x and y, and a hypotenuse of 4. See the following figure. Express the area of the triangle as a function of x. So first thing to note, what is the formula for an area of a triangle? I will not give that to you on a test. I trust in you. I believe you can memorize that one. So I will say it is 1/2 x times y. However, the problem is that it says express the area of the triangle as a function of x. Because I can't currently differentiate. I can't differentiate because there's just, too many variables. I can only differentiate if there's one variable. So what can I do? Well, I know Pythagoras' theorem here. If I look at how the y is related, I can say, okay, 1/2 x, I'm going to copy and paste that. Y is the same thing as the square root of the hypotenuse minus the x squared. So now it's entirely a function of x, and so that's good. All right, let us go and find the critical number. I'm going to take its derivative. A prime is equal to, well, what do we got here? A product. There's an x on the left, and a square root of 4 minus x squared on the right. So let's do our little product rule here. So first I'm going to go to 1/2. That's the derivative of the left-hand factor. Copy and paste the 4 minus x squared. All right, copy and paste now the x over 2, and now I'm going to take this derivative of the square root portion. That is 1/2 square root 4 minus x squared. Like, blah to the 1/2 is 1/2 blah to the minus 1/2, so that's putting it down there. Then times derivative of the inside via the chain rule, so minus 2x. And what are we trying to do? Oh, we're trying to find the critical number here. Isn't it 4 squared? Yes, of course it is 4 squared. Thank you. 4 squared, 4 squared, 4 squared. Wonderful. So now when I come here, oh, I see one cancel I can do. I got my 2's. I want to set this equal to 0. Now, I think a lot of people at this stage make an algebra error. Because here's the issue. We got the square root hanging down here on the bottom, right? Got that square root right there. But I can't set that easily equal to 0. So what I'm going to do is take that square root, and I'm going to multiply it up everywhere, where it's going to match exactly the thing I have over there, and it's going to bring everything together. I'll show you what I mean by this. So I also notice that I've got a 1/2 and a 1/2. I'm going to get rid of the 1/2s as well because it's equal to 0. So I can just multiply everything by 2. I'm just going to get rid of the 1/2, just to keep my life really easy. So the 1 square root and the other square root becomes a 4 squared minus x squared. And then I'm going to have a minus x squared. And then all of that's going to be equal to 0. See how I did that? That was me taking this denominator and multiplying all sides by that denominator. On the right-hand side, that was equal to 0, and so it was irrelevant. Okay, so what does that tell us? It tells us that 16 is equal to 2x squared. That implies that 8 is equal to x squared. That implies that x is equal to plus or minus the square root of 8. Did I make any other typos? It seems weird that I did square root of 8, not square root of 4 or something. Am I off by a factor of 2? If so, tell me in the chat. But for now, I'm going to say plus or minus the square root of 8. So those are critical numbers, but you got to be smart here. You got to be more than just solving the equation and getting whatever it spits out. Because let's go back and look up here. We're talking about a triangle. Negative x doesn't make any sense, right? So we're not going to say it is actually plus or minus. Let us come in and erase the plus. It is just going to be the value of 18. And we have to choose just the value of 18 because we want our distance to make sense. Other thing to think about here is, you remember how a critical number was where the derivative was 0? Or the derivative did not exist? Those were those two different cases. Well, look, the derivative does not exist here at the value of x equal to 4. Right? That's another spot where the derivative doesn't exist. It doesn't exist at the value of 4. Okay, is that a critical number? Well, let's see whether 4 is really in the domain. Let's scroll up. This is a triangle where one side length is 4. Imagine x was 4 as well. It wouldn't be a triangle then. It would be just two lines on top of each other. So 4 is not really a domain. It's an endpoint. It would be a minimum of some sort of ridiculous nonsense. So we don't include that point as well. So yes, it is a critical point of the function, but not for the setup that we actually have here. This area has a specific domain, and 4 is not in it. Okay. Then it says use the second derivative test or the first derivative test to verify that a has a maximum value at the critical number here. You can usually do one or the other. I never understand why anyone would do the second derivative test in a problem where you have computed the first derivative. I mean, I could go and do the second derivative, but why? Like, how would I be helping myself? I've already got the first derivative. Let's do the first derivative test. So we come along like this. We put our a prime, and we put in our square root of the value of 8. Okay? Now, I've got to figure out, is it going to be minus, 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 plus, plus, plus? Those are the two things I have to figure out. Okay, so let's go all the way back up to my derivative that I have up here. So I'm going to be looking back in at this equation all the way up here. So here's the way I try to figure it out. I want to say that, you know how there's a minus sign on this term here? And I got this big x squared here. If I make my x bigger, right, so I start increasing this thing here. Well, the term on the left here, right, that left term starts going down here. As your x gets bigger, this thing gets smaller, right? And then this negative thing here, yeah, I've got x's on the positive, but because of the negative sign, it's also getting smaller. So either way, it's going to be a minus, minus, minus on that side. And the converse argument tells that it's plus, plus, plus on this side. That's how I figure it out. If you want to, you can say, well, square root 8 is, a little bit of a bigger number would be like, say, 3, because that's square root 9. And then you could plug in 3 into this equation everywhere. It's just kind of, I don't know, it's a bit messy, so I prefer to be like, well, what would happen if it's a bit bigger or a bit smaller? Okay, plus, 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 minus, minus, minus. Is that consistent with it being a maximum? Yes. Increasing, decreasing. So this tells me it's a max. So please do something like that when you're trying to write it out. Do a little chart. Label it like this so I know which test you're doing, whether you're doing first or second derivative. Tell me whether it's the word maximum or minimum. Put that there. Put the root 8 in. By the way, this is a good verification for you. Suppose it was plus 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 on both sides. Okay, that could happen. It's plus 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 on both sides. What would that mean? Probably means you made a mistake. That your critical number is not right. So use this as a verification. Final thing, you have to answer the question that was asked. Here it says find the maximum value of A, where A is the area. So I've got to go and plug my A actually back into this. So I'm going to say that the area is equal to 1/2 times square root of 8. Is that really square root of 8? That seems just really weird, but whatever. Square root of 16 minus square root of 8 squared. So 16 minus 8. Oh, maybe this is why we made it that way, because that means it's a square root 8 times a square root 8. So it turns out to be an 8, so it's equal to 4. Okay, I guess it turned out to be a nice, pretty number in the end. I'm happy with it. All right. Let me know if you have thoughts or questions about that one. Otherwise, we're going to move on to something else. And let me know in the chat what should we move on to next. Number 4. All right. Oh, yeah, okay. I gotta go turn something's microphone off here. Oh, come on now. Just give me 1 second here. Got him. All right. I don't know why. I really like turning people's microphones off. It's just kind of fun. Okay, so let's go here. And I've got this thing. I want to find the equation of a tangent line. Equation of tangent line is just this. Y minus y naught equals m times x minus x naught. That is the formula you need to have memorized for equation of the tangent line. That is the so-called point-slope formula for the equation of a tangent line. But how do we plug it in? Well, we need to figure out the m, and we need to figure out the x naught, y naught. So the only one we know is the x equal to 2. That is the x naught. That is going to go in right there. For the m, we have to take the derivative. Let's take the derivative of the value of x first. It's a quotient, so let's do the quotient rule. So we have a 2 divided, oh, excuse me, I don't know how to do the quotient rule apparently. It is a derivative of the top times the bottom minus the top times derivative of the bottom, just 1, all divided out by x minus 1 squared. All right. We could clean this. Yeah, let's do it. Let's clean it up. So we got a 2x and a minus 2x. That's going to cancel. We have a minus 2 and a minus 1. Looks like a minus 3 over x minus 1 squared, if I've done my math correctly. And then if I do f prime, I want to plug in the value of 2 here. So plugging that 2 in, the bottom just becomes 1. It looks like I just have minus 3. Okay. So that's going to be giving me the slope now. So I can come here. That slope is this minus 3 value. The final thing I have to figure out is what is the y naught. So to get the y naught, I want to be going and doing the f of 2, the original function, the y, right? The original guy. So what is this? Plug it in. 2 times 2 is 4, plus 1 is 5, divided by 2 minus 1, which is 1. And so this is 5. And so final story, y minus 5 equals minus 3x minus 2. All right. And do we see that on the, oh, I don't quite see it on the answers. Oh, here's the problem. My answers are all written as y equals mx plus b version. Mx plus b is the stupid version, but sometimes we put it that way just so that it sort of obfuscates the intelligent guessing, if that makes sense. Anyways. Oh, actually, I guess you know what? Oh, look how clever this is. There's only one right answer, right? It has to be the value of c because that's the only one with the slope. I didn't even need to figure out the other number. So that was nice. I mean, I could have taken the 5 over. It looks like I had a plus 6. And moved the 5 over. That gives me the 11. Because of the minus 3, as soon as I got the slope of minus 3, I would have been done. Wow, we were super nice to you guys last year. My goodness. All right. Questions about that one, let me know. But other than that, moving on to number 12. Yeah, go ahead.
I have a quick question.
Yeah, go ahead, Ethan.
You noticed with 21, with how you did it,
yeah.
You would put it, so the hypotenuse was 4,
Yeah.
When you put it into your equation to substitute out y, it looked like originally you had put it just as 4, not as 4 squared.
Oh, I understand. No, you weren't wrong. I added that sort of halfway through my, like, as I was going through it, someone pointed it out and I went and squared everything. So you would have missed it when I was doing it the first time. You're not at all wrong.
Okay.
You're absolutely correct. My Pythagoras should be square root of the 4 squared minus the x squared. Thank you.
Okay.
All right. What are we going to? We're going to 12. Oh, no, can't do 12. We've already got 12. I'll put up the recording of the video. I'll put it here for just one moment here. But you will be able to get it in the recording version. Okay. 1 second. I can't see who won. Did 9 win? Is that the winner? 9 wins. Okay. Find the, okay, 1 second. I've given you, I love these problems. These are always my favorite problems. Okay, I've given you the derivative. I've given you the f prime. All right. And then I need to find the integrals on where f is concave down. Okay, so what does this mean? Concave down means the second derivative of the value of x is less than 0. That's what it means. Okay? In other words, because I have given you the first derivative, the second derivative is a little bit like saying it's the derivative of the first derivative. So in other words, the slope of f prime is negative. All right? So what I have to do on this little chart mobob thing is figure out, well, where is it sloping down? And it's sloping down right there. That's where the derivative is sloping down, aka the second derivative is negative, aka the function is concave down. Notice, by the way, there's those 3 layers. A function is concave down or up, its derivative is increasing or decreasing, and its second derivative is positive or negative. So there's the positive, negative, increasing, decreasing, concave up, concave down. Those are those 3 different levels of it. Okay, do we have that answer? -1 to 1. There it is right there. Wonderful. All right, after 9, I saw something here. 14. All right. 14 is one I want you to be on the lookout for. I want you to be hoping that you see it and to sort of be, kind of going there and recognizing it if you do. Anyone that involves the derivative of one of these integrals where up in the limits of integration are actual values, or sorry, not the opposite, not values, are variables, this is going to be a fundamental theorem of calculus problem. I don't always put the ddx out the front. I might do something like, I'll give you an example. I might say like f of x is equal to this, and then somewhere else I would go f prime of x, is equal to blah. Like I might hide the derivative somewhere else, but whatever. All right. All right. So for this method, fundamental theorem of calculus 1, the idea and the most common mistake is that you need to use the combination of the fundamental theorem of calculus with the chain rule. So what are we going to be doing? Sorry, I have to silence my brother. I want to be doing the derivative of the outside, e to the t squared plus 1. All right. Oh, I'm sorry. I lied. E to the, I'm going to leave a hole there, squared plus 1. But what I'm going to do is I'm going to put in the top function in where that hole was, where the t squared 1, I'm going to come along and I'm going to put an x squared in. This is like me doing the derivative of the outside, which just cancels the integral. Evaluating it at the inside, which means plugging in that x squared. And then this is the most important part, the part everyone always forgets, times the 2x, which is the derivative of the inside. Then I want to subtract, because I have to do this bottom here, I have to do the bottom x. So then I subtract the e to the blah squared plus 1, all right? But now I am just putting in the function of x, and I won't write anything, because, well, the derivative of x, of course, is just going to be equal to 1, so I don't have to bother with that if I don't want to. So that's my final answer. Okay, let's see if we have that somewhere. 2x e to the 4x plus 2x minus, I think this one matches everything. I believe answer D. All right. Seven. I always like, by the way, when I see people in the chat who are clearly not from my section, I think one or two of the other sections maybe open it up as well. So welcome non-Trevor section people. Okay. Oh, I remember this problem from last year. It actually caused a lot of problems, more problems than I anticipated. I think it's because there's a weird negative that slips in there because of the way the directions are working. So a man is running west towards a point P. So this person up here is running towards the point P. They're going that direction. Wonderful. And then a woman is running south away. They're going this direction. All right. At a rate of 2 kilometers per hour. Find the rate of change of distance between them when the man is 4 kilometers east and the woman is 3 kilometers south. Okay. So here's the big sort of thing. We have to figure out, there's a 2 kilometers per hour and there's a 3 kilometers per hour. But the 3 kilometers per hour, that's the one associated with the man, is a negative because they're getting closer to this point P, right? It's a negative. The 2 kilometers per hour, they're going away from the point P, so it's a positive. So yeah, they're both written as 3 and 2, but one implicitly is negative, one implicitly is positive. Okay, anyways, the formula here is the following. I want to measure that distance. I will call it d, and we can say that my d squared is the same thing as my x squared plus the y squared. When I take its derivative, it is 2d, d prime equals 2x, x prime plus 2y, y prime. I can make a little song out of it. I have a 1-year-old, so I'm getting really used to like little sing-songy things out of everything. So 2x, x prime, it's all good. So what do I know here, and what am I trying to figure out? Find the rate of change of distance. Okay, so the d prime is the thing that I really want to know. I know the x prime and the y prime. I know the x and the y. Do I know the d? I think I do, or I could figure it out at least. So let me change colors for a moment here. If I went and tried to figure out, oh, I can't change that. Whatever, is what it is. If I wanted to figure this out where I actually plug in the values of x, so x, the man is the 4, so that's 16. And then the y is 3 squared, so that's 25. And so the d is going to be equal to 5. So I actually do know that this d prime is equal to, I'll divide out by the 2d, so divide out by the 2 times 5, okay? And then the value of our x here is going to be this 4. And then the x prime here, this is the trick where I said it's going to be this value of this minus 3 here because it's going towards the point. And then I have a plus I owed a 2 there as well. So 2 times 4 times this, then 2 times my y. What's my y? My y is a south, so it's going to be a minus 3. That's 2 beneath this thing. And then what am I finally doing here is, where's my final number? Final number is a 2. Compute it all out, find the final value. All right. That's 7. 9, please. Nope, can't do 9. Done that already. Oh, I know. We can hear my son in the background. Yeah, he's not having a good day. He's been as sick as I was on Friday. 9, if you want to see 9, I'm just going to put it up here, but it will be in the video, and I'll timestamp it so you can go and click the video and find out where we want to go. But we can definitely go on to do 11. That is 100% a fair game. Poor little monkey. Just so sad being a little baby. Okay. And this is another one of these ones where you can almost hope that I give it to you. It's just a matter of recognizing the category. I literally cannot make this problem any harder than this one. I can just give you different functions. But what should I do? It's a logarithmic differentiation. How do I know it's logarithmic differentiation? Well, it's a blah to the power of blah. There's an exponent there, right? X plus 1 all up to the power of x. So what do we want to do? I will take that logarithm of y equals logarithm of x plus 1 all to the power of x. By the way, I remember one year we asked the question like this, I think, x to the root x, and we didn't put the y down, and we just like asked ddx of x to the root x. For some reason, not putting the y down really confused people. I can't remember if we did or didn't do that this year, but regardless, pay attention to the idea. If there's not a y, put in a y. That's basically my idea. Anyways, derivative on the left-hand side, it goes to y prime over y. On the right, now this is not me doing my derivative. I'm going to do algebra before I get to my derivative. I'm going to take this exponent, this value of x that we have out here, and I'm going to put it down out the front to give me x times logarithm of x plus 1. So that's me using a little bit of like log rules to sort of cheat the system a bit. And then it's a product rule. Okay, derivative of x is 1. Derivative of x is long x plus 1. Or ln, as the Americans say, or log, as the mathematicians say, but I often like to say ln, so I'm neither. And then I will take plus an x, and then derivative of ln is 1 over x plus 1. Chain rule, derivative the inside, but the derivative inside is just 1 itself, so I don't have to do anything else. Okay. Final story, this is the part everybody forgets, no matter how many times I tell you. Somebody on this stream right now is going to forget, I guarantee it. You got to take the y, you got to multiply it up, the x plus 1 to the power of x, all times natural logarithm of x plus 1 plus x over x plus 1. There we go. And I want to do y prime of 1. So let me plug it in 1. So I got a 2 to the 1 log of 2 plus 1 half. All right. So it looks like 2 log 2 plus 1, and hey, that's one of the answers. Hey, we're doing pretty good. All right, my goodness, we are making some progress. I'm happy to keep going if you guys are. We did hit 5 o'clock, but that was just sort of, a random scheduling thing. Someone got a suggestion? Want to go somewhere else? Four and 16. Okay. I'm going to leave 4 open for just a moment here. We've done it earlier, so I'm going to timestamp it and go into the video, and you can pick it up later. But it was just the equation of the line, and then you found out the slope and went from there. But I'm going to speed it along because I've already done it. Let's go to 16. That's okay. I'll forgive you eventually. 16. Perfect. Okay. Another pi over 4. We had a pi over 4 earlier on in the exam when we had to do that arcsin of 1 business. So what's going on here? Well, looks a lot like a u-sub to me. There's some messy denominator. The derivative of sine of 2x is cos 2x, so that's good. Well, I guess twice cos 2x, but let's do a u-sub. So I'm going to say u is the denominator, sine of 2x plus 2. Denominator is usually a good choice for the u. Not always. Sometimes if it's like imagine for a moment it was like square root of that. I wouldn't set the entire denominator to be the u. I would only set the portion inside the square root. But often the denominator is a good choice for you. Just don't get married to your u-sub. Try, play around, see if it works. Du equals 2 cosine of 2x. I mean, you can get married to your u-sub, but it's up to you. We have that looking real good. And then here's the part that a lot of people forget. You got to figure out the denominator and the numerator as well. We got to figure out the u of 0 and the u of the pi over 4 portion. Okay. So the u of the 0 here is, if I plug in 0 in for sine, I get 2. Okay, what about pi over 4? Remember the triangle we saw earlier, that pi over 4, 1, 1, root 2 triangle? So what are we doing? We're doing sine, oh, I'm sorry though. I put pi over 4, but I don't have to do this triangle because it's actually sine 2x, right? So I actually don't need to do this triangle because it's not sine pi over 4, it's sine pi over 2. And I know that that one is the value of 1. So this is 1, and then plus 2 is going to make the value of 3. All right, so sine pi over 2 because of it twice. So what do we get? It's the integral from 2 up to 3 of, you see the remaining 2 that's hanging out here, but there is no 2 right there. So you have to divide out by it, so it's a 1/2. And then a du divided out by u, so the 1/2 comes along for the ride. This is, well, the integral of this is the natural logarithm of u. And then you evaluate between 2 and 3. So 1/2 of natural logarithm of 3 minus natural logarithm of 2. By the way, don't forget your natural logarithm always has absolute values around it. If you know your values are positive, like 3 and 2, you can relax them and make them round brackets, but only after you know. So when you do the antiderivative, it's absolute values. And is that an answer? It looks like it is. By the way, if you wanted to use some log rules and say this was log of 3/2, you can do that too. I don't mind, whichever you prefer. But I guess it's multiple choice, then you don't have the choice option. Okay, we got to a lot of this test. Where should we go to next? Any ideas? So we've been doing a lot of this final exam. Oh my goodness, I think we've hit. Have we hit every multiple choice? Not maybe there's a couple holes remaining, but we got a good number of them, and I think we got a lot of the written problems as well. Can we do 16? 15 was great. Yeah, let's do 16 just to get them all out of here. Here's another U-sub one. I think that what was I going to say? For average value, the big thing we can do. It's another pi over 4. There's pi over 4s everywhere on this test. Can't deal with it. Apparently that must be somebody's like favorite number. I'm a pi over 3 person myself, but whatever. So pi over 4, we got to do the average value. The average value is 1 over b minus a integral from a up to b of f of x dx. There we go. I have to do it in my 1-year-old sing-song voice. Maybe I'll do it next time. So what is it in this case? 1 over pi over 4 minus 0. Your b minus a comes from the interval. Oh, shoot. I erased it. 1 over, oh my goodness. 1 over pi over 4 minus 0. Integral from 0 up to pi over 4 of all of this nonsense, 10 cubed of x secant squared of x dx. Now, there's a problem for your U-subs. Remember I said don't get married to your U-sub? Date around, find the right one, then marry it. Because there's 2 real options here. You could allow secant to be your u, or you could allow tangent to be a u. Both of those would be reasonable, right? So secant could be your u, or tangent could be your u. Which is better? If I set secant to be my u, derivative of secant would be secant tangent. There would be a secant and there would be a tangent. Because of the tan cubed, though, there'd be extra tangents you wouldn't know how to deal with. So I'm going to set tangent to be my u instead. So let's do that. U equals, ooh, we're going for green now. U is equal to tangent of x. Du is equal to secant squared of x dx. And see how there is exactly secant squared of x dx there? As in, there is exactly the right number of them. All right. U of 0, tan of 0 is just 0. Tan is sine over cos, and sine is 0. U of pi over 4. I'm not going to draw it again, but you know the 1 root 2 triangle. So if we're going to be tangent of pi over 4, this is 1 over 1 from that 1 root 2 triangle. Somebody says, love the color change. Thank you, I appreciate it. We got to have a Christmas spirit here if it's red and greens, apparently. Okay, so what do we want to do here? 1 over pi over 4 minus 0 is 4 over pi. And you know what? Screw Christmas. We're going to go for something exciting. Here we go. Got an orange. Integral from 0 up to 1 of u cubed du equals 4 over pi u to the 4th over 4 from 0 up to 1 equals just 1 over pi, and looks like we got an answer over here. Perfect. Oh, people with their private conversations. It's all good. Okay, good. Next up, what should we do? '17. Oh, you know what? I was just thinking I really want to do the definition of the derivative problem. You know what? Let's maybe even call it. Well, maybe, I think it might be one remaining after this one. I can't remember. But yeah, let's do the 17. Oh, definition of the derivative. How I like you. Definition of the derivative is one of these things mathematicians like me, they really like. Like, we like developing mathematics out of the definitions and building these whole edifices of mathematics. So this is the type of problem that appeals to people like me. Let's change colors again. We're going to express ourselves a lot here. Oh, look at this dark blue. It's going to be wonderful. So f prom of x, or purple, I can't quite tell, is the limit as h goes to 0 of f of x plus h minus f of x, all divided out by h. Okay, got to know your definition, put it on your formula sheet, memorize it, have fun. Now, in this case, there's a little bit of a weird trickery because it is the square root of the 2 minus x. That minus sign screws up so many people. I remember grading this problem last year. Let me tell you, this minus sign caused more trouble than any minus sign I've ever seen before. So I'll tell you why. Okay, so f prime of x is the limit h goes to 0. So the latency of this mouse is really bad. You can see my m's don't properly form, but whatever. So f of x plus h, it is square root of 2 minus. Now here's how you deal with it. In place of the x, you put a bracket, and then you write x plus h. The tendency is to go minus x plus h, but it's not. It's minus x minus h when you distribute over the minus 1. Minus square root of 2 minus x. All right. And then divided out by h. Okay. Now, when we do a definition of the derivative problem, there's 3 types of algebra it might be. It might be a lowest common denominator. It might be a radical conjugate, which is what this one is. And it might be one of those ones that's like x squared or x cubed, where you just have to factor it out. So it's either factoring, radical conjugate, or lowest common denominator. This one, radical conjugate. By the way, you cannot use L'Hopital's rule. That would be cheating. L'Hopital's rule would be using the definition in the middle of a definition of the derivative. It would be horrible. Let's switch colors one more time, just for fun. It's getting late. What else can we do? 2 minus x plus h plus the value of square root of 2 minus x all over square root of 2 minus x plus h plus the value of square root of 2 minus x, all of that goodness. Okay, and then I got to multiply it out. Now, be a little bit careful while you do this. Look, we are doing a big multiplication of things. So, how does it work? Let's sort of do a little thing. I'm going to do these. I'm going to do these first 2 terms. They're going to come together. I'm going to do those first, second, the remaining 2 terms, and then the 2 cross terms, one gets a plus, one gets a minus sign. And so they're actually going to be canceling, so I don't have to deal with that. Okay, so limit h going to 0 of square root of, oh, I'm sorry. I don't want the square root, actually. They're going to multiply out. So 2 minus x plus h. And then minus 2 minus x. I'm going to put the bracket around that and the bracket around that, and all divided out by h times square root of 2 minus x plus h plus square root of 2 minus x, all of that good stuff. Okay. And then what do we want to do? Let's do a little bit of canceling. So I've got a plus 2 minus 2. I have a minus x, a minus minus is a positive x, so that cancels. And then I have, got to be real careful here. You see it's a minus h remains now. So minus h on the top cancels with the plus h on the bottom, but the minus sign that's in front of the minus h stays there. So limit h going to 0 of minus 1, because it was minus h, now the h cancels, so minus 1 over square root of 2 minus x plus h plus square root of 2 minus x, all right, is minus 1 over square root of 2 minus x, but there's 2 copies of that. When you send the h to 0, it's 2 minus x plus 2 minus x, so 2 copies of that. Final thing, you've got to the end of the proof. You can put your little QED box if you so wish. Say you've got the end of the proof, don't have to do that, of course. But what you should do is a verification. We can do the square root of 2 minus x because we know the chain rule. We can get that. That's the value out of that. And so you can always, you should leave the test knowing for certainty that you've been okay on your definition of the derivative, because you can go and do a verification. Make sure you've got your limits in the right spot. Make sure you've got your equal signs. Make sure everything's written out neatly. This is one where we have the so-called quote-unquote style points. We take points off if your style is bad, rightly or wrongly. All right, that's that problem. Any other questions that you guys want me to do? Type it into chat if there is something remaining from an obvious whole that interests people. And maybe, as I say, now that we're pretty much near the end of this test here. Oh, there are people still calling. I was thinking we'd hit them all. There's still holes. 17. Oh, 18. What's 22? Yeah. Yes, let's do 22. I'm all about it. Okay. 18 is the last free response. Okay, I guess we should probably do that one. 22 is a bonus problem. It's really, really, really hard. If you get that, everyone gets an A+. UNC doesn't even give A+. What a gnarly expression. Why do we have to do this? Why is it so gnarly? I don't want to do it. Okay, but I'm going to find it. I'm going to summon my inner motivation for for this problem late in the day. So we want to go do this derivative here. Basically, for any time I do an implicit differentiation, the way I think about it is that when you've got y's, then what you want to do is do its derivative. So you put out a little y prime by a chain rule after doing the derivative in the normal way, as if it was an x. When you have x's, you just do them the derivative in the normal way. So the y's have this sort of little specialness that they kick out these factors of y prime. I'll show you what I mean by that. Secant squared of 2y plus 2. Don't be confused. We're taking a derivative. I know that the antiderivative of secant squared is tan, but we're doing a derivative. So this is a chain rule. It is secant of blah squared. So it goes to 2 times secant of this thing, 2y plus 2. Then the derivative of secant, which is tan squared of 2y plus 2. Then times the derivative of the inside of this thing, which is, well, 2y goes to 2y prime. Gnarly. Moving right along. Plus, okay, 4x squared y, well, that's a product rule. There's a product of this x squared term and this y squared term. So let's do the x squared term first. 8x, copy and paste the y, plus 4x squared. Y goes to the y prime. Getting excited because we're getting close to done. E to the y goes to e to the y, and by chain rule, you get a y prime out there. So the idea is every time you go to the y, you do the outside derivative, and then you have to take the derivative of the y prime through the inside. You put out a factor of y prime. Now we're almost done, except this thing asks for dy dx, which is super annoying. But that's the standard. That's what you have to do. So you have to come through here, and you have to be like, okay, let's find a new color. What's exciting? What have we not done before? How about this one? Is it two things? Oh, it's two. Let's do it. Got a y prime there, got a y prime there, and got a y prime. 3 y primes. One term hangs out over here, and I will spit it out onto the right-hand side. And so I want to go and just sort of, I don't know, just kind of clean it up a little bit, I guess. So let's do this. I will write on the right-hand side a y prime, and then I'm going to put a big bracket. It's going to be all the terms that have stuff to do with y prime. So the first one is all of that stuff. That's got a y prime there. So 2 secant 2y plus 2 tan squared of 2y plus 2 times 2. Got it all in. Nice. Next one up is this term here. It looks like I've got a plus 4x squared times the y prime, and then I have this e to the y. I got to move to the other side, so it's a minus e to the y. The y prime is factored out the side, and the final thing is this 8xy becomes a minus 8xy on the other side. Oh my goodness, I don't know how to take derivatives. Wonderful. Tangent doesn't. The derivative of secant is not tan squared. What kind of garbled nonsense is this? Oh my goodness. Okay. Let's do a little correction there. Oh, this is gonna take a while to write out. Okay, the derivative. Let's be careful here. The derivative of secant is secant tangent. There was one already, so that gives a second version of it, and then I have a tangent stuck out there. So I can square this and tangent. Okay, it wasn't that hard to fix. Thank you. Derivative of secant is secant tangent.
Wait, how do you turn the thing on?
Oh my goodness, the people are hanging out. How do we shut them up? I don't know what we can do. Oh, I know. I see the linker VR. Oh, he's done for. He's muted. You can go watch him if you so wish to. Okay. Final thing, we're going to take our y prom and say it is minus 8xy, all divided out by all of that nonsense. I'm too lazy to write it down, but you guys can write it down as well. Bye, Anish. Hello. All right. So that's our answer for that. I might ask you to go and do something. How do you turn off my video? No, we just wanted to watch the whole time. I'm sorry, Ben. That's just the way that goes.
I turned it off.
All right. All right. I think, have we hit everything? Have we got every single problem done on this test? Look, we're only an hour and 20 minutes in. You guys got 2 hours. This is easy. And I was going slow. Oh, got 1 hole. Okay, got 2 holes. 3 holes. 4 holes. Okay, we had a few multiple choice. Anyone interested in one of these last multiple choice? Let me know if one of you guys is sort of hankering around for it. I'm hungry too, man. Like, what can I say? We all can't be happy. Let me also ask, if you want me to do one of these last ones, let me also ask, is there any other big picture questions? Like, are people have questions about what the test is going to be like, or a question from a different section, or is anyone sort of sitting there with some lingering, or like, how do I do problems like this? Has anyone got one of those kind of lingering problems? It doesn't have to be related to the actual test that we're doing. Ryan, of course, I'd be happy to take the test with you. I'd give you an F, but I would be happy to take it with you at any time. It would be my pleasure. I can't remember the exact numbers. It was something like multiple choices. Pretty similar to this last test here. What do we have on this last one? Was it 16, 17, 15, 16? Yeah, somewhere in there, in the 16, 17 type of numbers, and in the same sort of story, like 5 or 6 type of written response problems. My guess is we will not take you a full, or let me put it this way. It is not quite twice as long as a test 1, 2, 3, but it's getting pretty close to that for sure. We add a lot of multiple choice problems. The answers are not going to be posted anywhere, but I will post this video with timestamps so you can just go and click through and jump to just the particular problems that you want.
I didn't know that the video was on.
people were waving. Yeah, I think Ethan asked, evaluating limits using factoring lowest common denominator, and I'm going to add to his list the radical conjugate. I think all 3 of those would be absolutely fair game limits to ask. I will say that you often on those ones with factoring lowest common denominator radical conjugate can get away with L'Hopital's rule as well, because now you didn't have them back in the day, but now you have both. I would encourage you, like if it's an obvious square root, use radical conjugate. If there's an obvious difference of fractions, use lowest common denominator, because the algebra is sort of like designed by us to make it be okay. But in theory, you could try a L'Hopital's rule as well and see if it got any easier. To Cole's question, can we sketch a graph? Yeah, why not? That's a totally reasonable question. I think that was on a bunch of the previous year's finals. It wasn't on this particular previous year's final, but it was on a bunch of the previous year's finals. So that would be a fair question for sure. Other big picture thoughts or questions before we bow out here? Well, folks, it has been a pleasure. There's still a good large number of you guys hanging around all the way to the end. Thanks for coming. I'll answer these final questions for sure. Will there be a speed, velocity, acceleration problems? Yeah, I mean, it might not be speed, velocity, acceleration. We had that one problem. I think it was problem 4 or something like that. I remember we had one problem on here that was like a word problem. Let's see if I can find it. Yeah, we had this one with like a bacterial colony, but it's the same story. Like you get a rate of change and you have to figure out the net change or the total change or something like that. Speed, velocity, acceleration is a very standard example of this class of problems where I give you the velocity and ask you the net change, or I give you the acceleration, ask you the net velocity. I think we did that one on on the last year's tests, I believe. So yeah, absolutely, that would be a fair game question. If you're in my sections, I think I've bugged you a ton about doing course evaluations. So everyone's already done them. If you haven't, please do them. If you're one of these other sections, you're not one of my sections, do the course evaluations for them, not for me. Please do them. They're taken really seriously. If you haven't done the surveys, do those for tonight or for tomorrow night. Good luck. Have fun. Get lots of sleep. I'm going to end it here, and I guess I'm going to see you all on Monday, bright and early. All right, guys. Thanks so much.